All right, so welcome to the fifth video on dimensional analysis. So this is going to be continuing the previous conversation about unit conversions, but we're going to specifically talk about one case, which is the gas constant. So in chemistry, you'll see a lot of times this R thing pop up, which is a big capital R, and that's the gas constant. It has a ridiculous amount of forms because it has a lot of units, and people like to combine different forms of those units. So I'm going to show you that it's really easy to convert between these different forms of R if you just don't overcomplicate things. For example, let's start with the value of R I know. Um, and if you don't know what these units mean yet when I write it out, just don't worry about it. Remember that you can treat them sort of like variables from algebra. So if the units start getting confusing for you, just switch them out for, X, Y, Z, whatever you need. So this is one form of R that I know, where the units are liter atmosphere over Kelvin mole. So just a reminder, liter is something that measures volume, atmosphere is something that measures pressure, Kelvin is something that measures temperature, and mole is just an amount of something. So I'll give you what conversion factors we need, and I just need you to start thinking about how to connect the dots. So if you go on the Wikipedia page, there's a ton of different forms of the gas constant you'll see. This is only one of them. There's probably like 20 other ones that are listed on there. And just another reminder, sometimes you see this little dot in between units, and that's just there to show you that you have two separate units, so in this case, liter and atmosphere, that are being multiplied by each other. So now let's say that we want the gas constant to have units of, let's say I want to convert this to have units of meter cubed Pascal Kelvin mole. And this is probably a really common problem you'll see on your Chem 6B midterms once you start taking that. This idea of the gas constant becomes super important in Chem 6B, and you'll see this a lot. Okay, so how do I do this? How do I get here? Well, okay, so let's look at what we're starting with and what we're ending with and try to find what's changing. Well, okay, so I'm looking at this. I'm keeping Kelvin and mole in the denominator in both of them. So it looks like we're not changing that. But it does look like we're changing the units of the numerator, right? So let's take a closer look at those units. So both L, or liters right here, and meter cubed in our new term, they both measure volume. So if they're just different ways of measuring the same thing, in this case volume, then there's going to be some unit conversion between them. And that's kind of like how feet and meters both measure distance, but there's a conversion between them. So I'll give you that. So I'll give you that 1 liter is equal to 0.001 meter cubed. Which in terms of conversion factor, I could either write as 1 liter over 0.001 meter cubed, or I can write it as 0.001 meter cubed over 1 liter. Remember that which one of these we choose is just dependent on the problem we're doing. Okay, so, well, it looks like I can convert pretty easily from this liter to meter cubed, right? So let's just write that out. We have 0.08206 liter atmosphere over, I'll draw a little line right here so we don't mix it up, over 1. Remember that denominator is always 1, Kelvin mole. Okay, I got liters up top in the numerator. I want to get rid of them. So that means I have to have liters in the denominator. 0.001 meter cubed. Got it. Okay, well, liters cancel out. I'm left with my units up top. You can see are now meter cubed atmosphere over Kelvin mole. So I'm halfway there. And this intermediate answer is 0.1234820 meter cubed atmosphere over 1 Kelvin mole. Okay, so if you were confused about this, I'd recommend just going back through and treating this like an algebraic problem. If you're not comfortable with the idea of a meter cubed Pascal or a liter atmosphere, maybe just think of it as x, y over w and z. And just keep constant whatever units you called each one. Like if I called Kelvin W, I'd have to keep that constant. Or if I called atmosphere Y. Sometimes just using these unit names and causes the confusion in the problem. And if that's the case, I would just start switching out what the unit names you use are to these variables, because it's a lot easier once you think about it that way. So I haven't introduced any conversion that would affect the other variables, so they've remained unchanged, right? I didn't have a conversion for atmosphere or Kelvin or mole in my conversion factor, so those have stayed the same the entire time. So now we're going to convert atmosphere to Pascal. So I'll just tell you that both of those measure pressure. So once again, there's a conversion factor between them. So there is 1,001,325 Pascal in 1 atmosphere. So if we're writing that out as a conversion factor, it's 101,325 Pascal over 1 atmosphere, or, the other way around, the reciprocal, 1 atmosphere, 101,325 Pascal. Okay, so we just have to now get rid of atmosphere and turn that into Pascal. So we go back over here. Let's write out what we have. 1, 2, 3, 4, 8206 meter cubed atmosphere up in the numerator. Denominator, I have 1, and that's Kelvin mole. Okay, so I got atmosphere up in the numerator, and I need to cancel it out, so I need atmosphere in the denominator. So that's this conversion factor right here, 101,325 Pascal. Atmospheres cancel out, right, because they're saying it to the same power, and I am left with 8.314 meter cubed Pascal over Kelvin mole. So if you check back on the Wikipedia page, like I was talking about, sure enough, our answers match up with what we should be getting. So this is how you get this totally different. You see how you get this totally different number from what we started with, but that's all because we've changed our units. And these units, you got different conversion factors, and that totally changes what number you have. So the number should not stay the same after you do all these unit conversions. Let's do one more, because there's so many of these for that gas constant. So once again, let's start off with 0.08206. This is probably the most common form you'll see the gas constant used in your classes, because it's just very useful for the something called the ideal gas law. So suppose your professor wants you to find R in the units of, let's do liter torr per Kelvin molecule. So once again, we've looked at what's changed and what stays the same. Well, liter and Kelvin look like they show up in both of them, so those didn't change. Atmosphere to torr, both of those measure pressure, so I have a conversion factor between them. Mole and molecule measure the amount of things I have, so there's a conversion factor between them as well. So let's start off with this whole atmosphere and torr thing. So I will tell you that 1 atmosphere is equal to 760 torr. So practice writing your conversion factors. Torr 1 ATM. Okay. 0.08206 liter atmosphere. Sorry, I wrote that kind of far away. Kelvin mole. Okay, we got atmospheres in the numerator. We got to cancel them out in the denominator. So I'm picking this conversion factor. 760 torr. Okay, so liters cancel out. Atmospheres cancel out. I multiply the two numbers I have, and I'm left with 62.3656. Now for units, I gotta look. So up in the numerator, I got liters and torr. So that means my units are liters times torr over, and then the denominator, I have Kelvin times mole. Oops, forgot my 1 in that. Got a little bit lazy. Okay, so halfway there. Now we got to convert this mole thing, right? So 1 mole is equal to a very large number, 6.022 times 10 to the 23rd molecules. Conversion factor, once again, 1 mole over 6.022 times 10 to the 23rd molecules, or also the other way around, right? Remember, you can just flip these and they'll do the same exact thing. So we start with 62.3656 liter times 4 over 1 Kelvin times mole. Okay, well, mole's in the denominator in this case, so I need mole in the numerator for my conversion factor, which is exactly how I wrote it right here. So 1 mole over 6.022 times 10 to the 23rd molecule. Cancel out my moles, multiply my two numbers, and I get 1.04 times 10 to the negative 22nd, really small number. Multiply my units that I have in the numerator, which looks like I just have liter and torr. And multiply my units in the denominator, which looks like I just have Kelvin and molecule. So that's it. So you could have done this conversion in any other order too. You could have converted moles to molecules first and then atmosphere to Pascal. Whatever way you work is fine. Shout out to the associative property of math for that one, doing us a solid. So this sort of finishes like the more advanced unit conversions you would be seeing throughout your time taking introductory STEM classes at UCSD. If you have any more like advanced conversions, feel free to message Paths on Slack and whoever's running this channel at the time, and we'll post a response video trying to go over those more advanced examples. So for the next video, we're going to be talking about just more general rules, but a little bit more advanced general rules about units and how you use them in equations.